All right. Good morning, everyone. Thanks for joining us. My name is Bassanio Peters, and I am the Chief Content Ambassador here at SolidProfessor. And I'm excited today to talk about a new course that we've just released called Intro to Ansys CFX. Was created by one of our esteemed authors by the name of Brian Parrelli, who I'll introduce here in a moment. And if you're unfamiliar with the term author, it's part of the content author program that we've created here at SolidProfessor to help our customers and our members to learn more. The really vision of our organization and our company is to become an all-encompassing engineering resource for our members. And to do that, we need to work with outside subject matter experts to extract their knowledge and put it into the SolidProfessor format. And that's really the genesis of the author program, and we look for the top subject matter experts, and I'm super excited today to talk to our esteemed author, Brian Parrelli. So we will dive right into the presentation. So just briefly, what we'll talk about here is the agenda. We're going to sit down and meet our author. Our author will talk about what's covered in the course, and then we're actually going to play a series of videos from the actual library itself, where you'll learn about mesh generation, creating a model in CFX-Pre, running the solver, and then doing some post-processing on a CFX Solution. We'll talk a little bit more about who SolidProfessor is and kind of our vision. We have a special offer for everybody that is on the call, and then open up some questions for you, the customers and the viewers of this presentation, to be answered, but once again by our esteemed author, Brian Parrelli. And speaking of our esteemed author, I want to introduce Brian. Brian, say hello to everyone.
Good morning, everybody.
So Brian, I just wanted to take a moment and let you talk a little bit about your background, your experience, and that way you can kind of share with the users, a little bit more about yourself.
Okay. So I come from UCLA. That's where I was educated. And after getting my master's degree, I started working at Pratt & Whitney Rocketdyne. Now they're known as Aerojet Rocketdyne. So I was kind of born into the whole rocket engine aerospace industry and kind of learned my craft there. And from there, I decided to switch over to oil and gas, expand my knowledge base a little bit, get the chance to design a bit more machines. And so now I'm currently spending most of my time working at a company called LA Turbine, designing turbine and compressor stages for the turbo expander industry. And I also part-time consulting still with Aerojet Rocketdyne, supporting their hydrocarbon boost rocket engine, which has 4 separate turbines in there that I'm managing, and that's slated for a CDR with the Air Force early next year. I've been working in turbo machinery my entire career thus far, so most of my CFD experience is with specific applications in turbo machinery. And yeah, I look forward to sharing my knowledge with you guys.
Awesome. Thanks for that intro, Brian. And just quickly tell me, what was exciting for you about developing this course and, kind of sharing your knowledge with our members? What was the most exciting part of, the thought of being able to share this knowledge? What were some things that, maybe you struggled with that you're now passing on to the next generation?
Yeah, that's a very good question. So when I first started out in the turbo machinery business, it's generally dominated by a lot of older engineers that kind of did a lot of, 1D methods in the 70s and 80s. But now we're kind of we're turning that new page over with new engineers. So I had to learn a lot on my own, and there was a big, learning curve, especially as a lot of the new software with Ansys and other companies started coming in. We were expected to kind of learn it on the fly. But now I think we've reached a point where I can provide knowledge to you guys that will get you guys ahead. So like right after you get out of college, or even while you're still in college, you can take a course like this and go out into the workforce and really make an impact right away. Because a lot of times it's very difficult to find somebody to really train you the way you need to be trained in a lot of this software. And so if I had this opportunity back when I was in college, I definitely feel like it would have benefited me tremendously. So that was what excited me about this, was just the opportunity to help the younger engineers first getting started to really get ahead.
Awesome. Well, thank you for that, Brian. We greatly appreciate that and you creating this course. And I'm actually going to launch a poll question here. You know, this is an Ansys CFX, which is the CFD solution, but I wanted to launch the poll question and get some feedback and really ask, how many of you guys have actually used Ansys or are currently using Ansys at the present moment? And leave this open for questions here for a moment. And once we get closer to at least 75 to 80% of the response, we'll move on in the presentation. All right. Looks like a lot of people on the webinar haven't had exposure to Ansys yet, and this is a great opportunity to gain that knowledge, gain that information. So we're excited to be sharing this with you. Let's see. And then, by the way, all questions that are being shared in the chat window, I'm receiving them, and then we will get to the questions at the end of the presentation. So we have a section dedicated to the Q&A at the end. All right, so we're going to close this poll and move on in the presentation. Thanks again for everybody taking the question, answering the questions here. So this is just a little bit more about the course description, and I'll have Brian kind of take it from here and just tell you a little bit more about what you're going to learn in this course. It's an intro to Ansys CFX course, but I'll let Brian talk a little bit more about what you're going to learn and what you can expect from this course.
Okay, so before actually getting into the course flow itself, I kind of want to talk a little bit about, my background is not a CFD expert in the grand sense per se. Like I'm not going to spend this whole course talking about turbulence modeling and getting into great details. There are other people that can do that. In today's market, to be viable, you have to have a broad skill set. And in order for CFD to have a place in my process as a turbo machinery designer, process efficiency is what is most important for me. So what I'm going to teach you guys is how to integrate software like this into a design cycle. So this course is designed to make you think more like a designer. Ansys CFX is the vehicle for that, but with a lot of these Ansys products and other engineering analysis products, that's really the main goal, and that's what's going to make you a better engineer, is how to get the nuts and bolts out of the software and have it add value and not get too bogged down in the details. So more specifically, what we're going to start from is from CAD modeling. I'm going to teach you very quickly how to build meshes from CAD models in a very general sense, and then we're going to go right into the CFX program, where we're going to put those meshes in, assign boundary conditions, talk about some of the different models and equations to employ in there, and move on through solving some cases and post-processing the solution. So my goal out of this is to get you guys familiar with the mechanics of how to use the software and how to complete these design cycle iterations quickly and efficiently. And from there you will naturally get better at using this software over time, because it's very intuitive. So I don't want to get too bogged down into the details, but rather teach you guys how to do this in the minimum number of steps.
Awesome. That's great feedback, and actually what we're striving for with a lot of our courses is to give you the skill sets for you to be able, or give you the understanding of the tools, so that way you can apply them, and as Brian just alluded to, you can start to learn, because many of the softwares today are intuitive enough. You just need that foundation. So again, thank you for that, Brian. We will jump in now and actually start playing a few of the videos here. Brian, do you want to talk about briefly what's covered in this actual lesson and mesh generation?
Okay, sizing a mesh. I don't know if there's going to be the intro into what this is. This is the example that you're going to see throughout most of the course that we're going to be doing all this analysis on. It's just a section of rigid tube where we have an inlet located there at the top, and the flow just goes in, makes a U-turn, and discharges there at the bottom. It's just a good representation of a simple geometry that will allow us to, facilitate explaining all of this material. So in this particular video, we're going to talk about how to size a mesh once you've imported the CAD model into the Ansys meshing program.
Medium, and fine options. These are generic options for how to specify the grid resolution in your problem. For now, I'm going to leave the setting at coarse, which will help speed up the processing. The next step is to create an initial mesh, just so you have a visual of what the mesh will look like. To do that, I'll right-click on Mesh and select Generate Mesh. Now, as you can see, a coarse mesh has been defined for the model. If you take a look, you can see that even though the mesh is coarse, the resolution in the streamwise direction is actually not so bad. The main problem with this mesh is the resolution near the walls. You can see it's extremely coarse in these regions here, and I need a much finer mesh here to resolve this boundary layer as the fluid travels through this tube. To do that, I'm going to have to insert a mesh inflation layer, which we'll take a look at in the next lesson.
My apologies, everyone. I actually had hit mute before I started playing the video because I was coughing. I've been a little under the weather, so my apologies for that. Missed the first half of the video, but we will actually move on to the next one to respect your time. And again, my apologies. I will re-record this presentation, and we'll upload it online, and I will make that tweak and change to make sure that the audio is able to be heard in the first part of the video. So again, my apologies. So the next one is creating a model in CFX-Pre, and again, I wanted to, before we play the video, if you'd let Brian in a couple sentences kind of just explain what will be covered in this video in particular.
Okay, so now we've created our mesh and we've imported it into the first CFX module, the pre-processing program, CFX-Pre. So in this particular video, we're going to talk about how to assign boundary conditions to this model.
Awesome. All right. Without further ado, we'll get started. We're not on mute, so we will. Everybody should be able to hear the presentation. My apologies again for the first time.
In this video, I'm going to discuss the mechanics of assigning boundary conditions in CFX-Pre. I'll not go into very much detail at all, but rather show you how to set up the boundary conditions for this particular problem in the minimum number of required steps. So, continuing from the previous example, I've already defined the domain, rigid tube. Now I'm going to assign boundary conditions for that domain. In this example, I will have 3 boundary conditions: an inlet located here at the top, a wall surface located here, and a discharge location on the bottom surface. First, I'll assign the inlet. To do so, I go to the domain, rigid tube, right-click on it, and select Insert Boundary. In this case, I'll define the inlet first and select OK. The two options that I have to select are the boundary type and the location. In this case, the boundary type is an inlet, and it's going to try to select the correct one by default based on the title I gave the boundary. There are a number of other options, but clearly inlet is the appropriate type of boundary. So I'll select inlet. For the location, I have to select the surface associated with that boundary type. There are three surfaces in this problem. These are the three that I defined when I created this mesh: inlet, outlet, and walls. So clearly inlet is the correct surface. It highlights, indicating that it is the one I want to use. Under boundary details, I'm going to select a total pressure and a total temperature to hold constant at this location. Under mass and momentum, I'll select total pressure, indicating that I'm going to hold the total pressure constant at that location, and I'll specify 100 psi. Since there's heat transfer in this problem, I also have to specify the temperature here. So under heat transfer, I'm going to select a total temperature and hold the constant at 100 degrees Fahrenheit. Once I'm done, I'll click OK. Now you can see arrows pointing into the domain, indicating that I have defined the inlet correctly. It now appears here, under rigid tube in the analysis tree. Next, I'll define the walls. I'll click on rigid tube and select Insert Boundary. In this case, I'll call it walls and select OK. Just as before, it has correctly selected the boundary type and location. If it doesn't select it correctly, you might have to manually go in and change this. But in this case, it clearly selected the correct surfaces. Under boundary details, there are a number of options, but no slip wall is the default option. That is fine for this project, so I'm going to click OK. I can now see that the walls have been defined. The last part to define is the outlet. So what I'm going to do now is right-click again and select Insert Boundary. In this case, I'll call it the outlet and select OK. Just as before, it has correctly selected outlet for the boundary type and outlet for the location. And you can see it's giving me the correct location. Now at the discharge, all I'm going to do is hold the static pressure, or the average static pressure, constant at this location. So it's 100 psi at the inlet. I'm going to hold it constant at 80 psi at the outlet. And click OK. Now you can see the arrows are pointing in here and out of here. This indicates that this is a discharge, or an outlet boundary. As you've noticed, all of the default surfaces have gone away, and I have correctly defined the inlet, our walls, and the outlet. At this point, this problem is completely defined and ready to solve. In the next set of videos, I'll go over the different boundary condition types in more detail, so you can understand how to properly assign boundary conditions that will best represent your problem.
All right, so you see we're kind of walking you through these series of videos, and you're getting a good representation of what you can expect in this course that was put together by Brian. And next we'll move on to the next step in the process, which is actually running the solver. And again, Brian just briefly explained to our members and people listening in, what to expect in this video and what will be covered.
This is basically after we've finished building the model. I will open up the solver manager and begin running the case. So this is going to show you how to import the solver input file, partition the case if you're going to be using multiple CPUs, and just taking a quick look at the residual convergence behavior of the problem.
Awesome. All right, so we'll dive right back into this one as well.
This video will go over how to monitor convergence in a CFX problem. Recapping from the previous video, the solver input file, case1.def, was defined. and the problem was partitioned using parallel computing into 15 partitions. At this point, I'll start converging the case by clicking Start Run. After a few seconds, this screen will appear. On the right is a printout of the out file. This is a text file indicating the convergence behavior of the problem. This file will be written to the working directory once the case is converged. On the left, you can see a number of plots being created that are also an indication of the convergence behavior. The first plot is the momentum and mass plot. This is telling you the residual convergence of your mass, which is the red line, and your 3 momentum components, which are the other 3 lines as a function of your iteration. There is also a heat transfer plot and the turbulence plot. As you can see, as time goes on and as the iterations increase, the residuals are getting smaller and smaller. This is a classical behavior that you will see in CFD problems that are converging nicely. At some point, the convergence will reach a level where the problem should stop on its own, indicating that the conditions specified in the solver settings have been met. And that is just what happened now. This screen will appear telling you the solver run had finished normally. But before getting into post-processing, I'm going to check the convergence and understand how good and how well converged this problem is before moving on to the next step.
All right. And then lastly, we have one more video we're going to play, and it's actually following that next stage in the process, which is post-processing the CFX study. Brian, again, just briefly for people that are unfamiliar, can you highlight what will be covered in this video?
Sure. So now we've converged the case, but for this particular one, this is actually taken from a second hands-on exercise. So the geometry you see in this example is going to be different. It's actually an electrical circuit board with a heat source and some cooling fins. So that is a hands-on exercise that will also be covered in this course. And in this video, we're going to talk about post-processing this particular case.
Awesome. And then I wanted to just quickly note, please continue to ask questions. I've been monitoring them, and it looks like we have a lot of really good questions for Brian and myself to answer at the end. So please keep the questions coming in the question box, and we'll get started with this video.
Welcome to the final video of hands-on exercise, number 2, in which I'll post-process the results of the electrical box CFD problem. I've already opened CFD Post here, so I'm going to go up to File and select Load Results to load the results file, and select electrical box _001.res. This file was created when I converged the case. You can see the outline of the geometry has now been imported. A quick tip for rotating and manipulating the geometry. If you want to snap to any normal axis, you can simply click one of the 3 default axes, and it will snap to normal to that axis. To rotate about that axis, you can simply hold down the control button and move the mouse up or down. So in this case, I'm going to rotate it this way. And I'll zoom out a little bit so you can see the whole thing. And this is actually useful because I want gravity to kind of point down in the field of vision so I can understand what's going on. So remember, gravity is pointing in the negative z direction. So this is a good view to have for this example for plotting. So the next step, of course, is going to be to create a cut plane so I can plot things on it. So as before, I'm going to go to the location selection and select plane. I'll just call it plane 1. And in this example, it's going to be a YZ cut plane. So I'm going to select YZ plane. And the location will be at x equals 0.2 inches, which will cut this model right down the middle. I'll click Apply. And you can see the plane has now appeared. Now I'm going to create some contour plots on that plane. So the first one I'll create is a temperature plot. I'll click the contour button and create a temperature plot. For the location, I'll select plane 1. And under the variable, I'll select temperature. And I'll plot 25 contours and click Apply. I'll go ahead and uncheck plane 1 so there's nothing overlapping or plotting on top of each other. You can see under temperature there's a nice cool region here around the fins, and a little bit of a hotness around this heat source, but no major hot spots. You don't really want to see a huge temperature gradient anywhere in a problem like this because that would indicate a high thermal stress. So this is actually a good sign and is what you would want to see. So now let's actually see what the velocity is doing in this problem. What I'm going to do next is to duplicate this temperature plot as a velocity plot. So I'll go right-click on temperature and select duplicate. In this case, I'll call it velocity and select OK. Now I'll uncheck the temperature plot and double-click the velocity plot. All I have to change on it is the variable. Everything else will be the same. It says temperature because I duplicated it, so I'll just select velocity and click apply. You can see this one looks much more interesting. You can see as there's very low velocity here on the heat source, but naturally it speeds up as it goes around this location here, and it slows down a little bit more here. So it's giving you a good overall picture of where the velocity is high and low, but it's not really telling you a lot about the direction. So I'll now create a vector plot to give some indication of what the vectors are actually doing. So to do that, I'm going to click this button here for vector. I'll just call it the default vector 1 and select OK. For the locations, I'll select plane 1. As far as the sampling, for now I'll just leave it as is. But under the color, instead of coloring it by a variable, which I've already done with the velocity, I'm just going to leave it a constant color. And this is sometimes useful when you're only interested in seeing the arrows themselves and not coloring them by any variable. You can actually specify, by clicking this button, what color you want for those arrows. And I'm just going to specify them as black. I'll click black, select OK, and click apply. And this looks quite busy as before. So remember what I did last time. I can actually select, instead of vertex sampling, equally spaced sampling. And I'll do 1,000 vectors to start with. Now it looks much cleaner. I'll zoom in a little bit and see what's going on. You can see that the fluid is actually rising up away from this heat source and really speeding up around here and turning around these fins and then coming back down, where it's getting hot again and cycling through. So that's what the velocity field is doing. So remember, gravity is pointing down, so as the fluid heats up, we would expect it to go up. And then as it cools back down, we expect it to go back down. And that's exactly what's happening here. So the last thing I'm going to do for this post-processing exercise is to create an expression to determine what the maximum wall temperature is on this model. To do that, I'm going to select Expressions, and I'll right-click on this region and select New and call it Tmax Wall. And click OK. In the Definitions box, I'll right-click, and under Functions, I'll select Max Value. In the parentheses, I'll right-click again, and under Variables, I'll click Temperature. Finally, I'll right-click again, and under Location, I'll select the outer walls, and click Apply. You can see there's an outer temperature of 533.3 Rankine, which is approximately 73.6 Fahrenheit. So that's indicating that the maximum outer temperature is just a few degrees above what the fin temperature was indicating, that this is a very good design and there's nothing to worry about. The temperature on the wall is not very hot at all, so I'm pretty much okay with this, and I'm ready to call this design done. And that's pretty much it. I hope this exercise was instructive, and I hope it taught you something a little bit different than a typical forced convection flow. But natural convection flow would look something like this. That concludes hands-on exercise number 2.
All right, everyone. So that's the last of the videos we're going to play, but just to kind of summarize, we went through and taught you guys in Ansys CFX how to create a mesh, how to set up the study. We actually ran that study, and then we showed the post-processing. That was actually one of the exercises in the lesson to post-process that study. Move on, and this is again just this Ansys CFX course, this Intro to Ansys CFX course really just helps us with our vision, which is again to become that all-encompassing engineering resource. We're trying to provide these next-generation learning tools for schools, individuals, large companies, small companies, and it's a mixture of our self-paced, conceptually taught lessons, and then the exercises like the one we just went through. And what we're really trying to do is help to democratize the knowledge in the industry. Again, become that Swiss Army knife for you to turn to when you have any questions, whether you want to learn something from start to finish, or just use SolidProfessor as an on-demand resource, which some people do. You're up against the gun. Pull up one of your questions in our search bar and see if you can get an answer specific to your application. So again, this is really kind of our vision, and adding this Ansys CFX course is really helping us on that vision and working towards our goals. So thanks again to our esteemed author, Brian. And what we'll do for all of the members that are listening in now, if you're not currently a member, sign up for SolidProfessor today, and you can receive 20% off an individual or a team subscription by using the promo code there, ANSYS20. Again, it is ANSYS20. And now we will actually open it up to questions. So what I'm going to do, everyone, is I'm going to read some of the questions from the dialog box itself, and questions that I can handle, I'll handle, and if not, I will pass it off to our esteemed author, who is the expert, Brian Parrelli. Let's see what we got here. Here's a good one. Will in the future CFX and Fluent merge? And how does someone choose between CFX and Fluent? Great question. Brian, I will leave that one to you.
Okay, so as you know, Ansys has two CFD packages, Fluent and CFX. As far as general solver capabilities, it's mostly a matter of personal preference, but there are certain advantages and drawbacks to each, and there's actually a lesson about that in the course. But in a nutshell, I would say for turbo machinery and conjugate heat transfer, those are where Ansys CFX excels. And also, I feel Ansys CFX is a little bit easier to use and easier to learn. On the other hand, for very large models, ones that are extremely complicated with multiple components, like you have a full solid assembly that you want to be analyzing, Fluent tends to handle those types of cases a little bit better. As well as if you have chemically reactive flows, like say you were doing a combustor design or something like that, CFX can sometimes be a little finicky with those types of cases. So in a general sense, if it's turbo machinery you're looking at, or simple fast turnaround time, CFX is probably the better one, and Fluent for chemically reactive flows. But as far as them merging together, I don't know. That's not a question I'm able to answer.
Great. I got another one for you here, Brian. Great question, by the way. Would you let's see. Would you know the pressure drop? What if you don't know the pressure drop? Excuse me. And can you assign a constant volume flow?
If you're solving a compressor case, I assume, yes, I do solve compressor cases here. Typically, I will employ either a constant pressure boundary condition on the inlet and the exit. But yes, you can assign a constant mass flow. You're asking about a constant volume flow, but if you're assigning it at one location or another, yes, you can specify a constant flow boundary at either the inlet or the discharge when you're solving a compressor case. It actually works extremely well for those types of cases.
Awesome. Another one, what is the sufficient convergence criteria for a CFD flow?
For really fine, it really depends, I guess, on what you're looking to do. Again, I come from a turbo machinery background, so for me, the settings I typically use for those types of problems in CFX are 10⁻⁴ for all the residuals, and 10 to the minus 4 for mass, momentum, and energy as well. There are other criteria that you could employ if you're looking for specific things, say like really high viscosity meshes and things of that nature. But in a general sense, 10 to the minus 4 is kind of the number I use, and I usually don't have too big of a problem achieving that using CFX.
Great. And then we have other couple of questions revolving around the differences between Fluent and CFX. Brian already covered those, so we will move on to the next question, which is actually a great follow-up to the previous question. What are the key strengths of CFX in aerodynamics, turbomachinery, electronics cooling? And by electronics cooling, I mean really hard problems like server cooling. Good question.
Yeah. Okay, so that's a two-part question. I'll start with the turbomachinery part. CFX, as far as implementing it into your process flow, if you are a turbomachinery designer, it's definitely pretty hard to beat. There are other options out there by companies such as Numeka and Concepts NRAC that offer these full design suite packages, but I find Ansys to be beneficial for turbomachinery because you also have Workbench that comes with it. So all of the structural analysis and the modal and resonance analysis, the rotor dynamic analysis, Ansys is very hard to beat in those areas. There are other companies that can compete for CFD, but I find that having CFX and having the whole thing integrated within Workbench is a huge advantage for a turbomachinery designer. What was the other part of that question, Bassanio? I forget.
Questions on, key strengths for aerodynamics, and then the other part was the electronics cooling, specifically hard problems like server cooling.
Right, okay. So for electronics problems, now CFX, this is actually something that's quite unique to CFX. It's able to solve what's known as conjugate heat transfer problems, which are coupled convection and conduction problems. So you can actually have multiple domains within a CFX problem where you have solid parts as well as fluid regions. So you can actually specify materials, say, a copper coil or something like that with some fluid going through it, and it has some thickness and some conduction through that wall, and then you have fluid on the outside. So you can actually model all of this stuff together all within CFX. So when it comes to electrical circuit cooling and things of that nature, it's extremely useful, especially if you're looking to design first simple models to kind of flush out bad design. You can actually set up some pretty meaningful cases and get some really good solutions rather quickly with CFX, and then kind of move on to the more complicated problems.
Great. So a couple questions I'll address. One, where can you download the webinar? We'll actually send out a link to everyone that is subscribed and subscribed for this webinar with the link to the video, so you'll be able to have that on hand. And then another question is particular to certification. We do have some certification prep courses for like, SolidWorks, CSWP, EA, and we're looking to expand that into other areas. And then we're also excited about a new tool we'll be launching next year that is not necessarily a certification, but it'll be a SolidProfessor branded way to be able to show off the skills that you learn. Then it aggregates the data from your actual lessons you've viewed, you've watched, and the tests you've taken in our platform. So that's something that's exciting that's coming out next year. Back to questions for Brian, and we can only answer a few more, and what I will do is take some of these offline as well, because I do want to respect everybody's time, but the number of questions that are coming in are definitely high quality, so we will try and stick around as long as we can. All right, here's a good one, Brian. Difference between SolidWorks Flow Sim and how do you compare it with CFX? I can take a stab at it, but I think you're more the expert to be able to answer that question.
I'm probably, for SolidWorks Flow Sim, I've actually never used that, so I'm not actually familiar with what capabilities are there. I don't know any engineers who use it, so I'll probably have to look into it and get back to you on that one. I can't really compare because I don't know SolidWorks Flow Sim.
Yeah, and I have some SolidWorks experience, so I can say that, Ansys CFX is a little more high-end of a tool when it comes to solving complex problems, but SolidWorks Flow Simulation is a great tool to getting you closer to the answer you need. So a simulation-driven product design, right? So you want to do the analysis up front to be able to help you come to a better conclusion. So using 3D and using a flow tool, just like many of the SolidWorks simulation tools, they're powerful for even some structural and that type of thing, but it's really a matter of the best way SolidWorks positions those tools is being able to use them up front in the design process to be able to optimize your designs, where CFX can do the same thing, but CFX will also, I wouldn't necessarily say give you better results, it's just you can handle more complex studies.
Right.
Let's see what other ones we have.
I can actually add a little blip to that,
sure,
if you don't mind, Bassanio.
Yeah, absolutely.
The advantage of CFX, if you're talking about a flow sim or optimization, you actually can have your SolidWorks model imported into the workbench, and you can continuously revise that model and repeat the analysis over and over again. So all you need to do is go into SolidWorks and tweak the model, and everything else, all the analysis will update. And this is very high quality analysis, like Bassanio had said. So yeah, when you combine CFX with Workbench, it's very, very powerful in that regard.
And one of the other questions that was in there that's a good dovetail is where else can I learn more Ansys? And I would assume that someone is referring to Workbench. We're actually in the process of developing those courses now. So be on the lookout. We will be launching some Ansys Workbench training material and tutorials in the very near future. It's kind of the part of my job is understanding what customers are asking for and what customers need, and then being able to identify the right subject matter expert like Brian here. And speaking of which, before we do close out this webinar, I'd like to launch the last poll, which is, tell us a little bit more about what you want to learn. Obviously, Ansys is identified as a key area, but there's some other tools that we're taking a look at and are actually in development. So I wanted to launch this poll question and see what feedback we get. And while the poll question is running, I will get some other questions answered. Can CFX be used for determining the amount of airflow or condensation in airflow, for example, knowing the dew point for temperature, for instance?
Yeah, in short, the answer is yes. To simulate, two-phase flow, CFX does have that capability. It tends to be very problem-specific, so I would need to know a little bit more about exactly what you're trying to model to tell you how easy or difficult that would be. But CFX does have fluid, it does have the capability to model both liquid and vapor states together in the same problem. Yes.
Great. All right. So with that, I will close everything out. Thanks again, and I will leave with one of the questions. Was a funny one I thought I'd share, and it is, where can Brian? They want to know where and how they can work with you at LA Turbine. So obviously the knowledge that you shared shows that you are a subject matter expert in this field. So again, thanks everyone for joining us. Brian, thank you so much for helping us develop this course. It is again part of our vision and our mission to become an all-encompassing engineering resource for you guys to turn to when you have questions or you want to learn something new. So with that, I leave you and bid you farewell and say happy learning. Enjoy the rest of your day, everyone, and we will be on the lookout for the next webinar for our next course release, which should be probably sometime in the beginning of the new year. So don't chat with you. Have a happy holidays. Brian, again, thank you so much, and we will see you guys next time around.
Thanks, everyone.